Hey, this is just dedicated to question 134 in chapter 3, and basically this is an opportunity to look at all the different kind of advanced solving techniques we've been looking at. The goal is for you to be able to do problems like this independently. So if you think you have an idea about where to proceed or what you should do next, go with it. Hit pause on the video and do your best to independently get to a solution. I'm here, you can watch these just kind of as an aid, but always the goal is for you to be able to do problems like these on your own. And the bigger goal is for you to be able to approach any kind of problem and have some idea of where to start and what sort of things you might try. So this problem kind of represents the one of the techniques that we've looked at that involves rewriting portions of the equation. On the right hand side I have a binomial times a binomial, and for now probably the best way that you can do this is to visualize this as a generic area model. So you may want to look at 3x minus 3 along the top, and then 4x, and then positive 8. So when I multiply these binomial expressions, I get the following product. Part of my product is 3x times 4x, which is 12, and x times x is x squared, so 12x squared. Next I have a negative 3 times a 4x, which is negative 12x. Below, in the left box, I have a 3x times an 8, which is positive 24x. And then my last box is 8 times negative 3, which is negative 24. So I'm going to rewrite the left-hand side using the values stored in those four boxes. Before I do that, though, let's look at what's on the right-hand side. On the right-hand side, you can see I've got 11 x's, and I'm adding to that an additional x. This is addition. If I have 11 of something and I add another one, that gives me 12 of them. So not multiplication here, this is 11x squared plus another x squared. So this is 12x squared. And on the other side of the equation, if I look at all four of the boxes, I have 12x squared, I have a negative 12x, I have a positive 24x, and the last thing I have is a negative 24. And you didn't see me write that because I didn't write that, so let me write that again with the pen turned on. So I have 12x squared, and then minus 12x, that's the upper right box, and then plus 24x, that's the lower left box, and then minus 24, that's the lower box on the right. So as I proceed to the next step, one of the things I notice is that both sides have a 12x squared. So I'm going to take away 12x squared from both sides. And it's really important as I do this that I recognize that on the left-hand side I have subtracted 12x squared from 12x squared, and what I have is I have nothing, but the symbol we use for that is 0. So it's really important not to just write nothing or leave it blank, because what normally happens, what I can see happen, is that students forget that this is an equation and my left-hand side is 0, and then that equals the right-hand side. On the right-hand side now I have negative 12x plus 24x and minus 24. So on that right-hand side I can combine the negative 12x and the positive 24x. That would give me that 0 equals a positive 12x minus 24. And what I could do now is I could go ahead and add 24 to both sides of this equation, giving me that 24 equals 12x. And then finally I'm going to divide both sides by 12. So on the left hand side, when I divide by 12, I have 2, and on the right hand side I have x. So x is the number 2. The second question allows us to practice fraction busters. If I look at my denominators, I have a 3 and I have a 9. And if I multiplied through both sides by 9, that would completely obliterate both fractions. So I'm going to multiply both the left-hand side and the right-hand side by the number 9. It's often convenient to write that as 9 over 1, especially if you've got fractions you're multiplying it with. 9 over 1 is the number 9. And on the other side, we're just going to multiply it by just 9, which is still 9 over 1. As I distribute this 9 to the two terms inside of these parentheses, right? In the first case, I'm left with 9x over 3 minus 9x over 9. And on the other side, when I multiply 6 times 9, I get 54. Well, if this isn't busting up the fractions, what's the point, right? But the thing is if you look at each of the fractions now, I've got 9x over 3, which simplifies to 3x. The next thing I have is 9x over 9, which is simply x. And then that equals 54 still on the other side. So 9x minus x is 2x, and that's 54. And if I divide both sides by 2, I get that x is the number 27. I didn't show this in the last problem, but these are pretty simple to to check. So for example, if I take this 27 and plug it into the original equation, x minus 3 over x minus 9, and see if that really does equal 6. In the first case, 27 divided by 3 is the number 9. In the next case, I've got 27 divided by 9, which is the number 3. And yes, 9 minus 3 is 6. So I can see that both the left and the right hand side become 6 when I plug 27 into this equation. The next problem gives us an opportunity to, I guess, rewrite it. But so when we see problems that involve exponents with variables in them, the one technique that we have in Math 1 is to rewrite it so that our bases are the same. And if you look at the number 6, normally I'll start with the smaller of the two bases, and I'll just play around with it for a while. So 6 to the 0 power is 1, 6 to the first power is 6, 6 to the second power is 36, and at that point I might stop, I might do some more, but this is the insight that I need. When I raise 6 to the second power, I get the number 36. And that's convenient because that's what I have over on the right hand side. The goal here is to rewrite it so that you have identical bases on both the left and the right hand side. And after that, we're going to set the exponents equal to each other. So let's take care of the equal bases first. On the left hand side, I have 6 raised to the power of x plus 9. And over on the right hand side, I know the number 36 rather, is 6 squared. So I'm going to rewrite that as 6 squared and then raised to the x. So you can see I haven't changed anything, I've just rewritten 36 as 6 to the second power. I'm actually going to rewrite it again, so I'll rewrite this as x plus 9 equals, on the other side I've got 6 squared raised to the x power. Well, when I raise a power to a power, I end up multiplying these exponents. So this is 6 to the 2x. And if you're not convinced of that fact, right, ask me to explain in class why is it that I'm multiplying here when I have a power raised to a power. And I can show you a couple numerical examples and probably convince you that this is true. At any rate, the only way that these two expressions can indeed be equal to each other, now that they have the same bases, is if their exponents are actually equal to each other. In other words, I need to force x plus 9 to be the same thing as 2x. And the way that we can do that is just start by asserting, hey, let's make x plus 9 the same thing as 2x and allow algebra to do its magic. This is not that difficult. If I subtract an x from both sides, I get 9 equals x, right? Because I took away an x from each side. 1x minus an x is 0 x's, so I'm left with a 9 on the left-hand side, and 2x minus x is x on the other side. So x has to be the number 9, and if you have a scientific calculator, you can plug in 6 and then raise to the power of, and you can actually do 9 plus 9 in parentheses like that and press enter. On the other side you can take 36 and raise that to the 9th power also and press enter, and you're going to see that you get exactly the same thing on both the left and the right hand side. Here's another opportunity to use fraction busters. If I look at this, I can see I have a 9, an A, and a 3. 9 itself is just the number 3 times 3. So if I multiply through by 2 factors of 3, it should neutralize the 9 and the 3. And to take care of the denominator of A, I'm going to multiply both sides by 9A. So if I do that, I'm going to go ahead and place parentheses around both sides. And again, I'm intending to multiply both sides by 9A. I'm going to write it as 9A over 1, so I'm not confused about how to deal with the fraction times a fraction. On the left-hand side, I'm going to multiply 9A times 4/9, and then I'm going to multiply 9A times 1 over A. 9A times 4/9 I could write as 9 times A times 4 all over a 9. And I'm going to leave that for a minute. Plus, 9A times 1 is 9 times A over an A. And then over on the right-hand side, I have 2 times 9 times A, all divided by the number 3. If I go through and simplify these, my first term, 9A times 4 over 9, has a giant 1 of 9 over 9. So if I eliminate that, I'm left with just A times 4, or I would write that as 4A. On the next part, you can see there's a giant 1 in the form of an A over an A. If I eliminate that, I'm left with plus 9. And then over on the other side, this 9 is actually 3 times 3. So you can see if I take one of these 3's and the 3 on the denominator, I get a giant 1 there as well. So I'm left with 2 times a 3 times an A, or 6A. The way you can do that is go ahead and multiply 2 times 9, which is 18, and 18 divided by 3 is 6 also. Next, I'm going to take away 4A from both sides. That gives me that 9 is 2A. Again, I subtracted 4A. And then finally, I'll divide both sides by 2, giving me that 9 is either 2/2, which is a fine answer, or you can write that A is 4.5. Either one of these are fine for checking. If you were to look at 4 divided by 9 and add to that 1 divided by 4.5, and look at the decimal value you get out of that, you will see that that's exactly equivalent to the decimal you get when you take 2 and divide by 3. I think this problem illustrates looking inside as a method. If you look at it, I've got a square root of something. I don't know what exactly that is because there's a variable that's in it, but the square root of something equals the number 6. Well, I know my perfect squares. It's something that I found that easy to deal with. A lot of multiplications I really struggled with, multiplication tables, but like 2 times 2 is the number 4, 3 times 3 is the number 9, 4 times 4 is the number 16, 5 times 5 is the number 25, 6 times 6 is the number 26. I'm sorry, 6 times 6 is the number 36. And at that point, I'm going to stop, because here's the deal, right? I need to make this question mark be the number 36, right? What's inside of here needs to be 36, because the square root of 36 is the number 6. So again, looking inside, what I'm saying is, hey, this A plus 3, that's nice and everything, but I need the A plus 3 to be the number 36. And this equation allows me to figure out what A is so that A plus 3 is 36. And you can see it once it's written, it's pretty easy to identify. You need to subtract 3 from both sides, and we get that A is the number 33. So if A was the number 33 and I plugged it into this equation, 33 plus 3 would be 36, and the square root of 36 is 6. So that is our solution. Another example of perhaps rewriting this equation, as I look across here, I can see that all of these have tenths, right? 1 and 2 tenths, minus 2 tenths equals 3 and 8 tenths plus m. Well, if I multiply both sides, all terms on both sides by the number 10, I could clear those decimal numbers. It's not necessary to do this, but it does make it look, I think, more manageable. So for example, 10 times 1.2m is 12m. And then minus 10 times 0.2 would be 2. On the other side, that equals 10 times 3.8 is 38. And then finally 10 times m is plus 10m. So I have multiplied both sides, both the left and the right hand side, by 10, and I have exactly a nice looking equation without decimals at this point. I'm going to take away 10m from both sides. When I do that, I have 2m minus 2 equals 38. If I add 2 to both sides, that's 2m would equal the number 40. And finally, by dividing by 2, we get that m is the number 20. And this is the last problem I'm going to do. This says something squared is the number 9. Something gets squared, and it produces a value of 9. Well, I think one of the most immediate things I think of is the number 3, and it's certainly true that 3 times 3 is 9. Something that may be less obvious is that if I take a negative 3 and I square that, I would also get the number 9. Negative 3 times negative 3 is positive 9. So using this look inside method, I need this number x plus 12 to be one of two things. I would like x plus 12 to equal a positive 3, and if that's the case, if I take away 12 from both sides, I would get, let's see, 12 minus 3 is 9, 10, 11, 12 is 9, so x would equal negative 9. So again, what I'm saying is that this x, if it were the number negative 9, negative 9 plus 12 is a positive 3. Negative 9 plus 12 is positive 3. And when I square the number 3, I get the number 9. So one of my answers is x could be negative 9. The other answer is maybe even more surprising. If I have x plus 12 and I want that to be negative 3, because again, negative 3 squared is also the number 9. I could take away 12 from both sides and I would get that x is equal to negative 15. So if I plug negative 15 in for x, I end up with negative 15 plus 12, which is a negative 3. And again, we've seen that if you take negative 3 and you square it, you get the number 9. So my solutions here are x can be negative 9 and x can be negative 15.